Welcome to this video on classical mechanics. I'm Jos Thijssen and I teach the second year's classical mechanics course at the Delft University of Technology to second year's applied physics students. In fact, the topic of this video is not strictly classical mechanics, because I will not only be dealing with point particles moving under the influence of forces, but I will primarily, in fact, explain how you can extend the variational techniques that you use in classical mechanics and the Lagrangian formalism to different applications. And I will go into one application which I will treat as an example, and that's the brachistochrone problem. And the brachistochrone problem is an interesting problem which is the solution to the curve, which should be designed such that when it runs from one fixed point to another fixed point, a ball running down that curve and which is only subject to the gravitational force should reach the lowest point in the shortest possible time. So I hope you will enjoy this movie. This video deals with variational calculus. A well-known example of variational calculus is classical mechanics in the Lagrangian formalism. This formulation centers around the action S, which is defined as an integral of the Lagrangian L over time, and L is a function of the generalized coordinates qj and qj dot, which are the time derivatives of the functions qj. And these coordinates, these qj's, they represent the degrees of freedom of a mechanical system which may be subject to a set of constraints. And the time evolution of the qj, which obeys Newton's equations for classical mechanics, is found by minimizing the action. And the action depends on these functions qj of t. So we try to find the minimum of S as a function of the functions qjt. And so S is also called a functional. So a functional is a mapping which assigns to each function or set of functions qj of t a real number by calculating this integral, by evaluating this integral. And we know exactly how to solve this problem because the solution is given by the Lagrange equations of motion. We have one equation of motion for each generalized coordinate qj, and they read total derivative d dt of the partial derivative of L with respect to the qj dot is equal to the partial derivative of the Lagrangian with respect to qj. And if we solve those equations, in fact we solve Newton's equations of motion for a system that may be subject to constraints, and these constraints are handled by D'Alembert's principle. Now we would like to apply the techniques of classical mechanics to different problems such as thermodynamics, optics, or problems even in mechanics which do not involve directly solving the equation of motion. But before we turn to applications, we want to point out that it's also possible to solve for the minimum of the action or the minimum of any functional, not by solving the Lagrange equation of motion, but if we can identify conserved quantities, such as the energy in a mechanical problem, it turns out that there is a neat way to solve for the stationary solution. As an example of this, we consider a particle in one dimension, particle with mass m. The coordinate of the particle is x, and because there is no explicit time dependence, the energy of the particle, which is the kinetic plus the potential energy, is constant in time. And that allows us to solve this problem not as a second order differential equation, but a first order differential equation, because here is already an equation for x dot. So we can write x dot explicitly as a function of x, and we could try to solve the resulting first order differential equations. For most mechanical problems, this is a method that we seldom use because it usually leads to it is only a first order differential equation, but it's more complicated usually than the second order differential equation that we get from the Lagrange formulation. Let us now formulate the problem more generally. We are interested in a functional called j, and this j is defined as an integral, in this case not over time, but we call it more generally x, over the variable x running from x0 to x1, and instead of the Lagrangian we write the integrand as a function f, which depends on y and y primed, and y is a function of x. For this problem, the Lagrange equation, or which we now call Euler equation, is d dx of df dy primed is df dy. So this is the form of the Lagrange equations in classical mechanics. And now we consider an object called h for Hamiltonian, and h is defined as y primed df dy primed minus f. And we consider the first derivative of h, a total derivative with respect to x. So that gives us first of all y primed df dy primed plus y primed times d dx of df dy primed minus, and now we should be aware of the fact that f depends on y and y primed, so we need to use the chain rule. So we first get a df dy times y primed minus a df dy primed y double primed. Now we see first of all that in this expression the first term and the last term cancel, and the same holds for the second and third term, because if we use the Euler equation, which is up here, we see that this is just y primed times the left hand side of the Euler equation minus the right hand side of the Euler equation. So these two are 0, 2, and therefore we find that this is simply 0. And that means that this quantity, the h, which you may have recognized as the Hamiltonian, is a conserved quantity. And so we can indeed now use the fact that h is constant, and like we see up there, that's y primed df dy primed minus f. And this is a first order differential equation. So that was the mathematical background for the variational calculus, and now we will move on to consider the example of the brachistochrone. So here you see a picture of Bernoulli, who formulated the brachistochrone problem as a challenge to the mathematicians of his time. And sadly for him, Newton took only a few hours to solve the problem, and that was when he was no longer really very active as a researcher anymore. So what is the problem of Bernoulli about? Well, we consider 2 points in space. They are called A and B. And we want to make a track running from A to B such that a particle or a ball which rolls along this track will reach B when released at rest from A in the shortest possible time. So we could imagine that we draw a straight line because that's the shortest. The other option would be to, for example, first go down a lot and then go over via a horizontal track to B, because then we take advantage of the gravitational attraction in the first part of the motion, so the ball will acquire a lot of kinetic energy, and that will help it to traverse the horizontal track in the fastest way. So now we are going to solve this problem using the technique of minimizing functionals that we can do either via the Hamiltonian or via solving Lagrange equations, or Euler equations in this case. Let's consider this red track, which is a rather arbitrary track running from A to B, and we chop this track up into small pieces, ds. And now what we would like to do is find the time needed to traverse this little distance ds, and that time is called dt. And obviously dt is equal to ds divided by the velocity of the particle. And the velocity can be found from the fact that the total energy of the particle is constant. We know that a half mv squared plus the potential energy, and the potential energy is mgy, that's the height of the particle. Now it may be better for this problem to choose the y in the negative direction, so that's the unit vector, and that would mean that we get a minus sign here. So if we increase y, that means we go down, then also the kinetic and then also the potential energy goes down, so the minus sign here is correct. If I add kinetic and potential energy, then we get a constant. And so we can find, just as before with the one-dimensional particle, that the v is given as E plus mgy, and then there is a factor of 2 over m, and we need to take the square root. So if we want to find the total traversal time, the TAB, then we can write that as a integral of all the small dt's. We add them up, and that's the integral along the path, and we can replace that by an integral of ds over v, and for v we use this expression here, 2 over m E plus mgy. Now the red curve can be written in the form y of x. It's just a height which is a function of the horizontal displacement. And if we take that form, it's easy to see that the ds is given by the square root of the x squared plus dy squared. That's a very general result which we will use quite often if we have a curve like this and we want to know the distance segment of a segment on this curve. Then we have on the horizontal axis a distance dx, on the vertical axis we have a distance dy, and so Pythagoras' theorem tells me then that the ds squared is equal to dx squared plus dy squared, and that immediately gives me this form. So if we then use this in this expression where we see that the ds is featuring, we obtain the following. We have the square root of 1 plus dy dx. I just take the dx outside of the bracket, and I can write that as y primed squared. And here we have the square root of 2 over m e plus mgy, and that is the problem I need to solve. Obviously the integral runs from the leftmost coordinate x0 up to the rightmost one, which is x1. Now we can simplify this integral substantially by realizing that we can shift the y component, and we can do that by changing the reference of the energy. It is well known that in classical mechanics it doesn't matter where we put the zero of the potential energy, we can put it anywhere, and we assume that the A point corresponds to y is 0, and we also assume then, or in our choice of the potential mgy, together with the fact that the particle is released with 0 velocity, so v is 0, we see that in point A, in the starting point, the energy is 0. So if y is 0, and at the starting point we see that the energy, the total energy, is 0. And so we can leave out the energy from this. So if we do that, then we obtain an even simpler equation, which reads 1 over square root 2g integral from x0 to x1 of the square root of 1 plus y primed squared divided by the square root of y dx should be minimized. In order to find the y of x which minimizes the time, we use the Hamiltonian formalism that we introduced before, and that tells us that the y primed times the f dy primed minus f should be constant in time. And so the f is precisely the integrand of the integral expression. And so let's take the derivative of this with respect to y prime. So first we have a y primed, then taking the derivative with respect to the square root gives me 1 over the square root of 1 plus y primed squared, and there's still a square root of y lurking around, and in the numerator we have a y primed squared. So in fact we have a y primed. When we take the derivative with respect to the square root we get a factor 1/2, but that is compensated by the 2 times y primed that we get from using the chain rule and taking derivative of this term. And then we should subtract from this the f itself, and this is our equation. This is the first order differential equation that we should solve. And we first are going to streamline the right hand side by giving the first and the second term the same denominator, which is 1 plus y primed squared square root of y. For the left hand, for the first term, we simply get a y primed squared, and for the second term we get a minus. We have to multiply that by the square root of 1 plus y prime squared, so we get simply a minus 1 minus a y primed squared, and we see that the 2 y primed squareds, they disappear, and so that enables us to write the equation that we should solve in the following form. Just by taking the square of the left and right hand side, the left hand being the constant, the right hand side being this expression, and renaming the constant and then taking the inverse, we get y times 1 plus y primed squared is a constant. So here you see the y times 1 plus y primed squared and that should be a constant, a different constant than there, but that means that the c has been renamed. And now the question is obviously how we can solve this equation. And usually if we see a 1 plus y primed squared, there are two possibilities. There are usually two useful approaches to take. One is to call this the hyperbolic sign. In this case, however, it turns out more fruitful to write this as tangent of phi. So we are going to substitute y primed is the tangent of phi, so that we obtain 1 plus tangent squared phi. The reason why this leads to something useful is that 1 plus the tangent squared of y phi is the same as 1 over the cosine squared phi. And so we see that y can be written as c times the cosine squared of phi, and we can also write that as c times a half plus 1/2 cosine of 2 phi. That's by a simple goniometric formula for the double angle. By simply inverting the resulting equation and then taking the square of the left and right hand side, we can easily put it in the following form. So y times 1 plus y primed squared is a constant. And then it's still not obvious how you should solve this equation, so we need to substitute something. And usually if you see such an equation, it can be useful to replace the y primed by a hyperbolic sign, or by a tangent phi. And so in this case we will take the last approach. So y primed, we call that the tangent of phi, and in that case we obtain y 1 plus the tangent of phi squared. And so why is it useful to take the tangent of phi here? That's because 1 plus the tangent squared can also be written as 1 over the cosine squared of phi. So that is constant. So we see that y is c times a constant cosine squared of phi. And by using a simple goniometric formula, we can also write this in the form 1/2 plus 1/2 cosine 2 phi. Now obviously that's not enough, because we would like to find y as a function of x. And the way we can do that is by calculating dx d phi. So we know how y depends on phi, and now we want to find out how the x depends on phi. And so if we calculate this, we can use the fact that x is a unique function of y, so we can use the chain rule. So we now use the fact that dx dy can be written as 1 over y primed, and we know what dy d phi is, because we can read that off from this expression, and it gives us first of all a minus, because the derivative of the cosine is minus the sine of 2 phi. Then the 2 here, using the chain rule, comes in front and compensates with the factor of 1/2, and there is a c. So in the end we see that we can write dx d phi in this form, and then we use the fact that we also know y primed. Because we know that y primed, we chose that to be the tangent of phi. So I can write this as a minus c sine 2 phi divided by the tangent of phi. Then we use the fact that the sine of 2 phi is 2 cosine phi sine phi, and the tangent of phi is sine phi divided by cosine phi, and so this then leads to the following equation for x. So using this these two goniometric formula, we can see that dx dphi is minus 2c cosine squared phi, and then writing cosine squared phi in the same way as we had done above gives me a minus c times 1 plus cosine 2 phi. Then obviously, in order to have x explicitly as a function of phi, we need to integrate, and that leads to a minus c. Then first we have a phi plus a sine of 2 phi with a half in front, and then there is an extra integration constant called d. So the solution is now given in a parametrized form. The parameter is phi. Here we see y as a function of phi, and this is x as a function of phi, and the solution is thereby given. So here I have repeated the expressions for x as a function of phi and y as a function of phi, and here you see a typical solution. So this is the brachistochrone, which brings you from A to B in the shortest possible time, and here you see a general solution. Now note that the scale on the x-axis is very different from that in the y-axis. If they would be taken the same, then this curve would be stretched a lot in the x direction, and it turns out that the shape that you see here is the shape, that's the path described by a point. If I consider a wheel like this, and suppose that the wheel is rolling over this surface, and I choose a point which is fixed on the wheel, then the path traversed by this point, that is given by this curve, and therefore this curve has the name cycloid. So the solution to the brachistochrone problem is a cycloid. So finally we have achieved solving the problem that Johann Bernoulli posed as a challenge to the mathematicians of his time. So this is a translation of his challenge as he posed it, saying, I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem whose possible solution will bestow fame and remain as a lasting monument. Following the example set by Pascal, Fermat, etc., I hope to gain the gratitude of the whole scientific community by placing before the finest mathematicians of our time a problem which will test their methods and the strength of their intellect. If someone communicates to me the solution of the proposed problem, I shall publicly declare him worthy of praise. And the problem was, the problem that we just solved, to determine the curve joining two given points at different distances from the horizontal and not on the same vertical line, along with a mobile particle acted upon by its own weight, so that's only a gravity force, and starting its motion from the upper point, descends most rapidly to the lower point. And the prize promised was not gold or silver, for these appeal only to base and venal souls, for which we may hope for nothing laudable, nothing useful for science. Rather, since virtue itself is its own most desirable reward, and fame is a powerful incentive, we offer the prize fitting for the man of noble blood, compounded of honor, praise, and approbation. Thus we shall crown, honor, and extol publicly and privately in letter and by word of mouth the perspicacity of our great Apollo. It must have been a little bit of a disappointment that Newton, who received this letter when he was a secretary of the Royal Society, succeeded in solving the problems just in a few hours during the night.